That roof is on fire. Oh, we gonna take it high.
Can you all read from this problem?
Yes, sir.
Okay. Good evening, everyone. I'm your tutor, Shata. So we are doing semester test 1 2024. So we are going to start with multiple choice, and it reads as follows. The first question, 1.1. Two identical small charged spheres are a certain distance apart, and each one initially experiences an electrostatic force of magnitude F due to the other. With time, charge gradually leaks off of both spheres. When each of the spheres has lost half its initial charge, the magnitude of the electrostatic force will be. So in this problem, we need to use Coulomb's law. Now, Coulomb's law says, can someone remind us of Coulomb's law? K
Absolute K
One,
value.
two, three, one.
one at a time, guys. Absolute of the sum of, product of the charges over R squared. Okay, so now we know that we are going to take the absolute value, meaning the charges of the signs of our charges does not matter, only the magnitude. Therefore, for the first part before the charge was leaked, the charge was just Q1, or let's just say the charge was Q, because it appears both of these spheres have the same charge. They are identical. Yeah. So we will have K, Q. I'm really not sure if the charges are the same. I just want to check. Two identical small charge spheres are at a certain distance, with each experiencing that due to the other. I'm not going to assume that the charges are the same. Let's just write them as Q1, Q2 over R squared. That's before the charge was leaked. And then they're saying with time, charge gradually leaks off both spheres. When each of the spheres has lost half its initial charge, the magnitude of the electrostatic force will be, so each sphere loses half, therefore we will call our new force Fn. So Fn will be half of Q1, and then F2 will be half of Q2 over R squared. Everything is still as it is, only half of the charges. Now the halves can multiply, and we can have 1 over 4 here multiplied by K, and then Q1, Q2 over R squared here. Now as you can see, this quantity here is the same as this quantity here, meaning our new force Fn is 1 over 4 of our original. Is this clear? Should we move on? Guys, a simple yes will suffice. Okay, now 1.2. The figure shows 3 electrical charges labeled Q1, Q2, and Q3, and some electric field lines in the region surrounding the charges. What are the signs of the 3 charges? So let's see. The first charge, the electric field lines are moving away from it. So remember, for a positive charge, it is radially away. So this is positive. And then the second charge, the field lines are radially inward. So that's what happens to a negative charge. The charges are inward or towards it. And then for the third charge, it is also radially away. So it should be a positive charge. Therefore, Q1 is positive, Q2 is negative, Q3 is positive, which is A. Are we all on the same page?
Yes, sir.
Okay. Now, question 3. A small class bit has been charged to 8 nanocoulomb. What is the magnitude of the electric field 2 centimeters from the center of the bit? So we have a bit somewhere here, and then it has some charge. Q is 8 nanocoulombs. Now they want the electric field 2 centimeters from the center of the bit. 2 centimeters, maybe somewhere here. Now, what formula could we use to find it? What formula could we use? Or what should be our approach towards this problem? You know, guys, I'll start volunteering people. You are too quiet today. So the formula for electric field KQ over R squared. Our K is 9 by 10 to the 9. Our Q is 8 by 10 to the negative 9. Our R is 2 centimeters. So that's 0.02, and then we square it in meters. What is this value, guys?
It's 1.8 times 10 to the power 5.
1.8 times 10 to the power 5. Thank you. So our answer is A. Shall we move on? Okay. Now 1.4 says at a distance of 4.3 centimeter from the center of a very long uniformly charged wire. So we have a very long wire here. And we are saying at a distance 4.3. At a distance 4.3 away from it. Let's say maybe somewhere here. That's 4.3 away. The electric field has magnitude 2000. The electric field has magnitude of 2000 and is directed towards the wire. Oh, so now I need to reverse this arrow that I drew here. It is directed towards the wire. And then what is the charge on a 1 centimeter length of wire near the center? What is the charge on a 1 centimeter length of wire? So they're saying on your wire, choose 1 centimeter. Choose 1 centimeter. And tell us the charge on that 1 centimeter. What is the charge on the 1 centimeter? So there's a formula for a charge, and that formula says charge, especially when we have a wire which has linear charge density lambda. Charge is lambda times the length. So if we are taking 1 centimeter of length, you would multiply your charge with your what? With your lambda. I mean, you would multiply your linear charge with the length. But we don't have the linear charge. We don't have the linear charge. We only have the electric field 4.3 centimeters away. So we need to link this linear charge density to the electric field. Now, there's a formula for the electric field of an infinite line of charge, and that formula says lambda over 2 pi epsilon naught r. It would be nice if you learn to derive this problem and not have to do what? To always cram it. You need to know where this formula comes from. But I will come and show you a shortcut on how to find it. But for now, let's find our answer. So we have these quantities, and what we are looking for is this lambda here. So let's make this lambda the subject of the formula by multiplying by our denominator on the left. We will have 2 pi epsilon naught r. Our electric field is 2000 multiplied by 2 pi multiplied by 8.854 by 10 to the negative 12 multiplied by our r, in this case, is 4.3. So you will take 0.043 in meters. Can someone tell us what the answer is here?
I got 4.78 times 10 to the negative 9.
4.78 times 10 to the power negative 9. So because they said it was radially inward, we can put a negative here to show that it is negative. And then, now that we have the linear charge density, let's find our charge. Our charge is then equal to our linear charge density, negative 4.78 by 10 to the negative 9, multiplied by our length of 1 centimeter, which is 0.01. Yeah. So what do you guys find?
4.78 times 10 to the negative 11.
Negative 4.78 times 10 to the power negative 11 coulombs. But our answers are given in nanocoulombs. So what we can do is, how do we change this, guys? How do we change this? You take the decimal place backwards. Remember, if you take it backwards, you are making this value smaller to accommodate for that add to the indices here. So if you want nano, you'll have 9 here. So that means we add 2. Therefore, we go backwards twice. 0.0478 by 10 to the negative 9. We added 9, we added 2, we went backwards twice. So our value corresponds to 0.048. Are there any questions before I derive this formula? If there is none, what we can do is to say, okay, this is an infinite line. So for infinite lines or objects, infinite line, infinite sheet, infinite something, we can use Gauss's law. So we can use a shape which is symmetric to our line, which is a cylinder. Our cylinder doesn't have to be infinite, it can be finite. So this is our cylinder, and we enclose our line in it. Now after enclosing it, we realize that there will be some flux into our cylinder, and that flux can be calculated using Gauss's law as flux of the electric field is equal to the closed surface integral E dot dA, which is also equal to charge enclosed over epsilon naught. Now, if we integrate, the area that we are going to have is the area of a cylinder, especially the area of its body. We ignore the caps. There's no electric field coming out of its caps. Like the electric field is radially away or radially inward along its body, not on the caps, for this infinite wire. So the area will be 2 pi radius for the circular part multiplied by the length. 2 pi radius for the circular part multiplied by the length of our cylinder, and is equal to the charge enclosed. But we know that the charge enclosed, we are not enclosing one charge, we are enclosing charge over some length, which is our linear charge. Our linear charge, therefore from the formula, our linear charge density is charge over length. Therefore on the left we have our charge enclosed as linear charge multiplied by length. Linear charge multiplied by length over epsilon naught. Now we can see on both sides we can cancel the L. After cancelling the L and dividing by 2 pi r on both sides, we have found our formula for the electric field of an infinite wire, 2 pi r epsilon naught, in the radial direction. Are there any questions? If there are no other questions, let's move on. Let's move on to 1.5. May I just drink some water, guys? My voice is fading. Okay, I am back. Now, for this problem, 1.5, it reads as follows. An electric dipole consists of the charge 5 microcoulomb separated by 1.2 millimeters. It is placed in a vertical electrical field of magnitude 525 Newton per coulomb, oriented as shown in the figure. The magnitude of the net torque this field exerts on the dipole is closest to, so we need to find the torque, and the formula for the torque is dipole moment cross to the electric field. Now what is the dipole moment? Guys, what is the formula for the dipole moment? QD, charge times distance between them, between the two charges. So it is usually referred to as a vector, and its direction, if this is our negative and this is our positive, the direction is from negative to positive. The direction of the dipole is from negative to positive. So this is the direction of the dipole. Now that we have that, we can say the torque is equal to QE sin psi, whereby psi is the angle between the electric field and the dipole. So in order to see the direction, the angle between the electric field and the dipole, we need to think of them in vectors. So our electric field is this way, our dipole is this way. What is the angle between these two? It is this 140, because these are vertically opposite. So we have this 140 here. Therefore, to find this quantity, we will take our dipole, which is QD, multiplied by the electric field and then by the sign between the two quantities. Now, our charge is 5 microcoulomb. Our distance is 1.2 millimeters, which is 1.2 by 10 to the negative 3. Our electric field is 525 sine of 140 degrees. Can you guys calculate this very quickly? Are you guys here? Do you even have calculators, guys? I'm getting worried. I got 2.024 by 10 to the negative 6, which is closest to A. Are we all here, guys? Are we all on the same page? You are awfully quiet today. I was expecting you guys to be more interactive. You already did this with your lecturer. With your lecturer's tutor. I was there in that session. So let's try to help each other understand this better by being very interactive. More interactive. So question 1.6 reads as follows. Consider a spherical Gaussian surface of radius r centered at the origin. Okay. This is our origin. And we are considering a spherical Gaussian surface of radius r. A charge Q is placed inside the sphere. We place Q inside the sphere. To maximize the magnitude of the flux of the electric field through the Gaussian surface, the charge should be located where? What is your answer, guys? Where should we locate Q such that we have more flux coming out? Where should we place it? We can place it anywhere inside. It doesn't matter where it is. because what we care about is the charge enclosed over epsilon naught, not where it is inside. So let's move on. 1.7. An uncharged conductor has a hollow cavity inside of it. Within this cavity, there is a charge of 10 microcoulomb that does not touch the conductor. There are no other charges in the vicinity. Which statement about this conductor is true? I got lost along the question, guys. An uncharged conductor has a hollow cavity inside. So it's a conductor, it has a space inside. It is uncharged. Within this cavity, there is a charge of 10 microcoulomb. 10 microcoulomb. That does not touch the conductor. There are no other charges in the vicinity. Which statement about this conductor is true? Before you even answer this problem, you have to remember that if there is charge in the cavity of a conductor, this charge is going to induce an opposite charge on the walls of our conductor. It's going to induce negative ones here. And then, because we have the negative ones here, these negative ones have to be cancelled out by the other positive ones that are induced outside, so that they cancel and the overall charge is just the charge that we originally had in the beginning. So this is how charge distributes in a cavity of a conductor. Now, in between, there is no charge. Why? Because charge sits on the surface of a conductor. It does not sit inside. Remember that. Except this one that you put here. This one that you put inside, it won't fly away. This is just the distribution, the induced charges. Now, which statement about this conductor is true? The inner surface of the conductor carries a charge -10 and its outer carries no excess charge. No, we have a charge outside, the induced one. The inner and outer conductors each contain this one is also lying. Now the net electric field within the material of the conductor points away. The net within the material, you see it says within, inside, is away. Look at it. Inside we have this charge that is induced. And if there was flux due to this induced one, it wouldn't even be away, it would be towards, like inside. So it is also not true. The inner material does not have such a charge that can induce the electric field to be outwards. And they are saying it is from the positive one. The positive one is going to give out flux outward, but not where they are saying it is, not within. Within means here, because it's hollow. They are saying here, which is not true. Now the outer surface of the conductor contains +10, and the inner contains -10. Now this one is corresponding to what we are saying. After this has been induced, the inner has negative, the outer has positive. Now E says both surfaces of the conductor carry no excess, which is not true. Are there any questions, guys, on this one? We say the answer is D. Let's move on in the absence of questions. 1.8, 3-point charges. 3-point charges, -2 microcoulomb, 4 microcoulomb, and 6 microcoulomb are placed along the x-axis as shown in the figure. Now, what is the electric potential at point P relative to infinity due to these charges? So you want what? You want the potential at P due to 1, 2, and 3 relative to infinity. Okay. Relative to infinity could also say if you calculate the potential due to 1, 2, and 3 separately and then add them up at a point P, what will be your potential? Absolute potential. Remember, when you want potential due to one charge, it's absolute potential, which could be relative to P and infinity. And remember, at infinity, we have zero potential. So the potential will just be for that point that you want. Okay. Now let's calculate this value. We might have to redraw this diagram on the next page. I don't have space here. So cram this diagram. We have negative 2, 4, 4, and the distances are 0 0.2, 0 0.2, and 0 0.2. I'm going to work it out here. So we have something like this. And this is point P, and upwards is 0 0.2. From here to here is 0 0.2. From there to there is 0 0.2. We have negative 2 micro, and then 0. Is it negative 2, guys?
Yes, sir.
Okay. And then 2 fours, positive ones. Now we want potential here. So the formula for potential, yeah?
The charge on the right, 6.
Oh, yeah, it's 6. Okay, thank you. So the potential is KQ over R. But if it's many charges, we can write it as the sum of those charges divided by the respective distances. So our formula then becomes K of Q1, Q2, and then Q3, which would be over R1, Q2 over R2 plus Q3 over R3. Okay, now we have 9 by 10 to the 9 multiplied by Q1, we could say it's negative 2 over its distance from P. What is the distance of Q1 from P? This distance. That's 0 0.2 and then 0 0.2. What is the hypotenuse of the two values?
It's 0.28.
Thank you. And then multiplied by 10 to the negative 6 because it's micro. Then take the second charge, 4 by 10 to the negative 6 divided by its distance, which is 0 0.2. 0 0.2. And then the third charge, 6 by 10 to the negative 6 over its distance, which is also 0 0.28. So guys, multiply, add, and then multiply.
I got 3.09 times 10 to the power 5.
Times 10 to the power 5. Did you all get the same answer, guys? Or you didn't even bother? We have 307. Oh, let's see. Okay, I think that was the wrong answer. I read the wrong answer. I don't know. 307 is closer. Yeah, 307 is closer. Is it positive or negative? Because we can rewrite it as 309 by 10 to the 3, which is 309 kilovolts. Positive or negative? If you inserted negative 2 as it is, then it is positive. Here we don't take the absolute value. Okay guys, should we move on? Are we still on the same page?
Yes, sir.
Guys, don't get lost and keep quiet. Stop me if you are getting lost. So let's move on to 1.9. It reads as follows. Two parallel conducting plates are separated by 1 millimeter and carry equal but opposite surface charge densities. If the potential difference between them is 2 volts, what is the magnitude of the surface charge density on each plate? Yeah, it was a long question. We have two plates. You know a capacitor, guys. Do you know a capacitor? A capacitor has those two plates. Positive charge above, negative below. Separated by this distance. We have 15 minutes left. Equal but opposite. If the potential is 2, so that's saying the voltage is 2 volts. What is the magnitude of the surface charge density on each plate? Remember, the surface charge density is given by charge over area, right? So what formula can we use to find that charge on the plates? What formula can we use? We can use Gauss's law here too, guys. Remember, we can use Gauss's law to find the electric field of one of the plates. We use a cylinder, and if we use a cylinder, okay, because this is a negative charge, there will be flux in from both directions. And then we are going to say the electric field is given by, okay, this is a shortcut. I don't want to use a shortcut. I was just going to give you the answer. Remember, we want to calculate it. E dot dA is Q enclosed over epsilon naught. But Q enclosed, remember Q enclosed when we have a surface, is the surface multiplied by the area. So this is going to be the surface multiplied by the area, surface charge density, guys, over epsilon naught. And the electric field will be just E, and our area will be the area of our what? What's our area, guys? Our area is the area of a circle. Our electric field is passing through a circle. So it is the area of a circle, but we don't really have to include that area. We can just write A so that it cancels with this A. This area and this area are one and the same. So we end up having the electric field. Okay, something that is very important to note is that you have the electric field on both sides. Like it's on the above part and on the below part, meaning we have two electric fields. This is very important to note because now we are going to say the electric field is sigma over 2 epsilon naught. And this is the electric field of a single plate, one plate. But here you have two plates, so you have to multiply it by 2 again. Or maybe think of it as adding 2 because you have two plates. So the formula you are going to use is the electric field. This is not going to be part of our answer if I write it here. So where am I going to write it, guys? I've run out of space. But you are going to use electric field is sigma over epsilon naught. And what are we looking for? Sigma. Therefore, we will find the electric field and then multiply it by epsilon naught to find the sigma, because we are looking for sigma in this case. To find the electric field, we can use the properties that are given by these two plates, and they are going to say the electric field is potential over the distance between them, and that potential is 2 over the distance of 1, which is 1 by 10 to the negative 3. What do you get here, guys? Whatever that you get, multiply by epsilon. That's our answer. Multiply 2,000, or is it 20,000? 2,000. Multiply 2,000 by epsilon. What do you guys get? I got 1.7 by 10 to the negative 8. 1.77, which is closer to 18 if you write it in nanocoulombs. How do you write it in nanocoulombs? You make this one bigger, make this one smaller. Now we have 17.7 by 10 to the negative 9, which is similar to 17 nanocoulomb, closer to 18 nanocoulomb. Are there any questions? If there is none, okay, remember that when we have electric field as sigma over epsilon naught, this is for two plates. Alright. Now, for 1.10, a metal cylinder of radius 2 mm is concentric with another metal cylinder. So you have a metal cylinder concentric with another metal cylinder. Concentric means they are doing this one inside the other. And then one has the radius 2 mm and the other has 5 mm. If the space between the cylinders is filled with air and the length of the cylinders is 50 centimeters, what is the capacitance of this arrangement? So guys, physics question paper is going to cheat you on Monday. This problem is very long. It's more than 2 minutes to do. Remember, 2 marks equals 2 minutes. it's more than 2 minutes to do. In fact, most of the problems that we did here, example, this one whereby we had to derive the electric field first, then a lot of these questions are too long for 2 minutes. So you need to be extra prepared. Extra prepared in a sense that you know these formulas. You know that when it's a capacitor, the electric field of a capacitor, because it has two plates, is sigma over epsilon naught. But if someone gives you a sheet, one sheet in space, and they're saying it has a charge, that sheet has electric field sigma over 2 epsilon naught. And remember, that sheet should be an infinite sheet. We don't know where it ends, such that we can use Gauss's law to find that electric field. So now here we have this cylinder. We first have to find the capacitance. We have to find the quantities that can help us to find the capacitance. Remember, the capacitance, if we were to just use its dimensions, this is what we would use. This is how we would just do this problem. But we can't in this case. We can't because, let's see, for one, we have this formula which says that in fact, we might try. You see, as I said, we can't, but we might try to use it. But usually when this is derived, it's derived from the formula that says the capacitance is, in fact, not the capacitance, but the charge is QV. So to find the capacitance, it's charge over voltage. So we need to find this potential difference first, and then divide that by the charge. So to find that potential difference, remember, you're going to say we have KQ over R, but in this case our charge, we need to find that charge first, and our R is changing. In fact, our charge can just be constant. Let's say the magnitude of our charge on both these cylinders is just Q on both of them. So we have KQ, but now we need to integrate, because our cylinders are long. We need to integrate 1 over R dr, which is whereby now we are going to have KQ ln of the radiuses that we have is 2 and 5. 2 and 5. 2 and 5. And then what are we gonna do from here, guys? What are we gonna do? I feel like I'm skipping some steps. I don't know which ones, but yeah. From here, we are going to say this is KQ ln of 5 minus ln of 2, which can be simplified to KQ ln of 5 over 2. Now this is our potential. After finding our potential, we need to find our capacitance. So our capacitance is Q over K Q ln of 5 over 2. And these guys cancel. So now we are left with 1 over K multiplied by ln 5 over 2. So guys, work this out.
See,
Yeah,
the Saturday test does not include capacitance.
or it does not. Okay, but ish, we are already done with this problem. I apologize for not being cognizant of that, but yeah, I should have. What do you get, guys, when you calculate this? I'm just curious. You're supposed to get a value close to 30. What are you getting, guys?
So I'm getting 1.21 times 10 to the negative 10.
Huh. Okay, I wonder why. I'm also getting that value, which is unexpected. I was expecting 30.